Hi everyone, welcome to the Earth Science Regions Review podcast series created by Hammock's Middle School Earth Science Department. Today we're going to focus our attention on radioactive decay. Now radioactive decay is a very, very important topic here because it actually helps us identify the actual age of a rock sample. Up to this point we've talked about relative age, which is basically comparing the age of a rock sample to another rock sample, telling you which one's younger, which one's older. This is a method that actually gives you the actual age itself, and it has to do with the breakdown of the nucleus. Whenever the nucleus of an atom starts to break down, we say that it becomes radioactive. It starts giving off charged particles. We can measure the charged particles and figure out exactly how old that rock sample or fossil might actually be. Well, we are familiar with radioactivity because we can harness its energy in a fuel source in these power plants. Now, in order to understand radioactive decay, you have to have an idea about the different parts of an atom. Well, we've already established that the nucleus is the brain of the atom. Okay, we have positive charged particles called protons, neutral charged particles called neutrons, and negative charged particles called electrons. And they're all going to revolve around the actual nucleus itself. Now, an isotope is going to be an unstable or radioactive version of a stable element. Okay, the stable elements you're probably going to be pretty familiar with because they're going to be found on the periodic table of elements. Okay, the big difference between the element on the periodic table and an isotope is the nucleus has a different number of neutrons. So when you look at the periodic table, you have a wide variety of elements here. What you want to look for is the number of neutrons in the nucleus. And there's basically 4 isotopes that you need to know. You need to have an idea about carbon-14, which is an isotope of carbon-12. You need to know a little bit about potassium-40, which is an isotope of potassium-39. You need to have a little bit of an idea about uranium-238, which on this periodic table is also uranium-238. And also rubidium-85. The isotope that you need to know is about rubidium-87. Now, these isotopes are going to break down, and they're going to break down within a certain amount of time. And what they're going to do is they're going to break down into what's called a decay product, or sometimes it's called a daughter product. And the way that you're going to figure out how old a substance is by figuring out the ratio between the isotope itself and what it's going to break down into, called the decay product, or sometimes called the daughter product. And what's going to be important here is what we call your half-life. Now, the half-life itself, it's kind of self-explanatory. It's the amount of time it takes for half of the isotope to break down into the decay product or daughter product. And that ratio between the decay product and the isotope will tell you exactly how old the rock is going to be. Okay, it's going to help us determine absolute age. So for instance, carbon-14 is going to break down into nitrogen-14. What's important about this, it's going to be used to date organic material about 50,000 years old. Okay, this has a relatively short half-life, and it's going to break down very quickly. So usually, because it has a short half-life of about 5,700 years, that isotope is going to be pretty much gone and pretty much non-detectable in about 10 half-lives. So you can see the Iceman here would be a good example of using carbon-14 to try to date how old that specimen is. Potassium-40 actually has 2 daughter products. It has argon-40 and calcium-40. This can be used to date very old rocks and fossils because it has a half-life of about 1.3 billion years. You also have uranium-238. That's going to change into lead-206. That's going to be used to date the age of the Earth because, relatively speaking, the half-life of uranium-238 is about 4.5 billion years, which is identical, that we believe is the age of the Earth. So uranium-238 would be very good in dating the age of the planet. And then finally, the last isotope is rubidium-87. That's going to change into strontium-87. This has a monster half-life. It's about 49 billion years. So obviously the half-life of rubidium-87 is definitely older than really since the Big Bang. The Big Bang occurred about 13.7 billion years ago. This stuff has a half-life of 49 billion years. Okay, it's almost out of that realm of being able to comprehend how long it takes for half of rubidium to change into strontium. So when you take a look at your decay rates themselves, they're very predictable and they're irreversible. Once you change carbon-14 to nitrogen-14, you can't change it back. Okay, and it's very predictable. That's why it's a very good time marker. Okay, so the physical factors have no influence on the decay rate. So if you go through and you change your temperature, the pressure, the mass, the volume on a rock sample or fossil sample, it will have no change on the decay rate of your isotope itself. So what's going to be very important here is to be able to identify the isotope and decay curve. So as time goes on, your isotope is going to lose mass and your decay product is going to gain mass. So when you look at those together, you can see along the horizontal is your half-lives, 1 half-life, 2 half-lives, 3 half-lives, and so on. And this is actually the half-life for carbon-14. Along the vertical axis is the number of atoms, okay, in hundreds. So you're going to start out with about 1,000 atoms, okay, of your isotope and 0 atoms of decay product. After 1 half-life, it's 50-50, so 500 decay product, 500 isotope. After 2 half-lives, you have 750 decay product and 250 isotope. After 3 half-lives, which is about 17,100 years, you have 875 atoms of decay product and 125 atoms of isotope. And as you can see, as time goes on, your isotope loses mass, and as time goes on, your decay product gains mass. So with that being said, hopefully you learned a little bit something about radioactive decay, and we'll talk to you soon.